You know, when we ask an AI to solve a problem, we usually expect it to go find the one single best answer, right? But what if that's not really what we want? What if, instead of just one perfect solution, we could get a whole collection of different, really high-quality answers?
So traditional optimization, it's kind of like climbing a mountain just to find the single highest peak. But this really fascinating new approach called quality diversity, or QD for short, it completely changes the goal. Instead of finding one champion, the idea is to build a whole library of many different champions, where each one is excellent in its own unique way.
And this is just a perfect way to picture it. Instead of one perfect photo of Tom Cruise, a QAD algorithm finds an entire gallery. You get Tom Cruise with short hair, long hair, you get him younger, older, a whole range of high-quality, diverse options. See, it's not about finding the best Tom Cruise, it's about finding every good version of Tom Cruise.
But, of course, building this library of solutions is a really, really hard problem. One of the most powerful attempts was an algorithm called CMA-ME. And while it was a huge step forward, researchers pretty quickly discovered it had some serious flaws.
Okay, so the research community really dug in and they zeroed in on three specific problems, three critical failures that were really holding this algorithm back from unlocking the true potential of quality diversity.
So the first flaw? It basically had a short attention span. It would find a new type of solution and get so excited about this novelty that it would immediately just run off to find another new type. It completely abandoned the job of making that first solution even better. It just favored exploring over perfecting.
The second issue was that it got paralyzed by choice. You know, on problems where there were tons of equally good solutions, what's called a flat objective, it didn't have a clear signal telling it which way to go. So it would just get stuck. It would stop exploring effectively.
And finally, it was just a bit fragile. Its performance really tanked whenever that library of solutions, what they called the archive, was small or had a low resolution. It just wasn't robust enough to handle different kinds of problem constraints.
So with these three really clear problems on the table, researchers developed a brilliant solution. They created a new algorithm called CMA-ME that was designed to fix all three of these flaws with one simple, really elegant change.
So the breakthrough is this new parameter they call the archive learning rate, or alpha. Now, the best way to think of it is like a dimmer switch for the AI's focus. All the way on one end, you've got pure optimization, finding the absolute best. On the other end, pure exploration, finding as many new things as possible. This switch lets the algorithm smoothly blend the two, and that, it turns out, is the absolute key.
And you can see that dimmer switch in action right here. When alpha is turned way up, the algorithm acts just like its flawed predecessor. See? It finds an easy solution and then immediately gets distracted, totally ignoring a better but harder to find solution over there. But when you dial that alpha way down to a low value, the algorithm suddenly becomes patient. It smartly spends its time finding that higher quality solution before it shifts its focus to go explore other areas. It's brilliant.
All right, so that's the theory. But does it actually work in practice? Well, the researchers put the new algorithm, CMA-MAE, in a head-to-head competition against the old one, just to see what would happen.
I mean, wow, the results are just night and day. On the left, you can see the old algorithm is just stuck in that tiny little corner, totally unable to explore the full range of possibilities. But look at the right. The new CMA-MAE has completely, beautifully filled the entire solution space.
And hey, remember that second flaw we talked about, getting paralyzed by choice? Well, this slide shows it's completely solved. The old algorithm on the left is just lost, wandering around aimlessly. But the new one explores the space perfectly. This is that annealing idea in action. It lets the algorithm keep moving and exploring even when it doesn't have a clear signal. It turns a major weakness into a massive strength.
And the crucial point here is that it's not just about making pretty pictures. The numbers absolutely back it up. Across a bunch of standard benchmarks, the new algorithm's QD score, which is a measure of both quality and diversity, is just dramatically higher. I mean, look at that. It almost doubles the score on some of these tasks.
Okay, this is where it gets really exciting. Because this breakthrough isn't just some theoretical improvement. It has huge practical applications, especially in the world of reinforcement learning, where we're trying to teach AIs to perform really complex tasks.
Check this out. In the classic lunar lander game, instead of just finding one single way to land safely, CMA-MAE discovers an entire playbook of successful strategies.
It finds ways to land straight down, or to come in at a really wide angle, or to hover first. It's a whole repertoire of solutions for mission control to choose from.
And it's the exact same story in slime volleyball. The algorithm doesn't just learn to win, it learns all the different ways to win. It discovers these aggressive, rapid-fire styles played right up close to the net, but it also finds patient, defensive styles based on these long rallies from the back of the court.
And this really brings us to a final, powerful question. We have spent so much time asking AI to find the single best answer. But what happens when we can ask it to find every good answer? This shift in thinking, from a single point to a whole landscape of solutions, could unlock entirely new forms of creativity and problem-solving we haven't even imagined yet.